I'll ask people to raise their hand. But Mark, if you don't mind, I might start with the first question. So it's a very impressive thing you've got going here, and with all these grand challenges and strategic leadership, and then opportunities which arise, like the monitoring of pedestrian spacing during the pandemic. So my question is, are you able to explain how you lead everybody involved in the Turing in the same direction? We're at a much earlier stage than you, and we're trying to bring together ideas from across disciplines and then have some sort of common underlying interest that drags us all in the same direction. How do you do it across so many institutions and so many big projects?
So I think, I mean, I guess I can only talk about how I've done it. And the first thing was really identifying these grand challenges. And the reason that I think the grand challenges and the articulation of them was so important is that they basically acted as concentration points for everything that we would do. And a grand challenge can be communicated to a geotechnical engineer, to an aeronautical engineer, to a functional analyst, to a stochastic analyst, to a computational statistician, to a materials scientist, and they can project what they see as important and what they see as they could contribute to these grand challenges onto them. So I think that was the first thing, was having very clear and crisp grand challenges. And then the second one was to have a leadership team that that I guess were open, were sufficiently senior that they were comfortable and not worrying about their next promotion or their next grant application, and so therefore could, in many ways, take the risk of saying, I'm going to go and sully myself by talking to these engineers or those engineers or what have you. I think that their leadership and their enthusiasm and energy was one of the ways of success. I mean, I have to say that I've probably poured all of myself into this. I have a natural tendency to get interested in loads of things. I mean, my background, I actually studied mechanical engineering at Glasgow, worked as an electronics engineer at IBM, and then kind of got into trouble, got into statistical signal processing, became a professor of computer science, and then of statistical science and mathematics departments, and I've ended up, as a chair in a civil engineering division. And so I think, leadership that really has the agility and real desire to understand things and realize that science and engineering isn't stovepiped. It does, cover. All of these disciplines are artificial in many ways, and one of the real beauties was seeing how a lot of the fundamental concepts really did underpin pretty much everything that we were trying to do. The other aspect, I think, from a leadership and managerial perspective, was the group leaders. So I mandated that the group leaders, if they wanted to be involved, that they committed themselves 100%. And that meant physically locating in London. So moving from Newcastle, locating in London, moving from Warwick, locating in London, moving from Cambridge, locating in London. And the reason for that was that I saw, when I first took on the role of director, that the 10 million was being held up as a pod of sweeties. And as we do as academics, we were sticking our hands in, taking out $500,000 and going and doing our own stuff. And so I stopped that and said that if you want access to these funds, then you need to absolutely commit yourself, get seconded from your home institution, come here to London and do this. And those that located in London, so there were statisticians, there were environmental engineers, there were architects, there were aeronautical engineers. And of course, what happened was they just started to talk to each other. They started to have coffee together. And before we knew it, this diffusion of ideas across disciplines, really had an advective component added to it. And we saw things that we, that would have been very difficult to do had they stayed in their home institutions. So that was probably quite a unique opportunity because there was the Turing and basically the funders said to me, do what you want with the money. And so that's what I did. And I think that really, pushed things along. So, being 100% focused on making this a success and having that responsibility for growth and not just spending down, doing a little bit of research, but reaching out. What was the other? I think that was probably the main thing that's the main aspect that has made this grow to the extent that it has.
That's really great. Thank you. Okay, there's a couple more questions at least. Now we've got Magnus and then Hugh. So Magnus, if you want to lead off.
Mark, thank you very much. Diffusive component added to it an advective component. I'm going to remember that. And, by bringing people together, that's absolutely beautifully put. Thank you so much. I guess the most of us on this call are already sold on the opportunities with data-centric science or engineering. Sometimes when I try to sell it to my colleagues, and the ones that are difficult to convince because they see it as end of science sort of approach, I say to them, well, I'm sure that if you go data-centric, you will learn fundamentally new things, but fundamentally new parametric relationships that you didn't understand. And then you can take a first principles approach and try to figure out what you learn from a data-centric perspective. And I heard you say, you talked about that in my ears, at least, when you said that you had two digital twins, you try to merge, and there were new properties that came out from that merger. Somehow that's what I heard you say, at least. My question is, do you have examples of a data-centric approach that have led to new knowledge in the fundamental space, that fundamentally led to new understanding of parametric relationships, scaling relationships, that makes perfect sense from a first principles approach as well?
So the way I like to describe the data-centric perspective is as follows. Think of Kepler. What did Kepler do? He gathered data. He had the greatest instruments available at the time. He watched the movement of the planets. He gathered data, and from that data inferred what the motions were. There were no underlying first principles. On the other hand, Newton, he came up with the first principles and allowed, this is what you would call science, and then allowed us to be able to predict, what those motions were. And so one is data-driven. Kepler was data-driven, and Newton was hypothesis or fundamental relationships driven. And if we think of science today, engineering science today, there are many phenomena that we just don't understand what the fundamentals are. Turbulent combustion, there's one example. Many exotic materials. you know, we don't have that understanding. But what we do have are ways in which to make measurements and gather data from them. And taking the two of those together, a fundamental approach where there is perhaps some notion of physics, some notion of underlying chemistry, but it's incomplete, and some way of making measurements and gathering data, one data-driven, one fundamental, and combining those in some way then gives us a data-centric perspective. So that's the way I kind of define data-centric. So the statisticians amongst you would think, yeah, okay, you know, the known science gives us a prior, the data gives us a likelihood, and the data-centric approach gives us a posterior in which we can, refine those hypotheses. So in terms of examples, I think one of the biggest ones, so, you know, we've only been on the go for the past 5 years. And as you know, making big leaps like that takes time. But I think the two areas where we are starting to see progress in a data-centric view, starting to fill in the gaps of the more fundamental descriptions, is in the theory of turbulence and in material science. And I can talk more at length about those with you offline. So I wouldn't say that it's the end of science. I would say that it's the acceleration of science, because data provides us with additional information and additional insights.
Okay, Hugh, you have a question.
Yeah, I want to get Mark to talk a little bit about some of the key, I guess, theoretical, taxonomies in here. I mean, we've had about 6 months in our group of hearing from some great computational engineers, including turbulent combustion, now that you mention it, in Matt's area. And we see a whole set of fairly common equations. That's what's interesting, to do with either fluids or solids or networks or particles, and there are definitely families of these. And there are mechanisms that these communities have adopted to solve these equations. Again, finite elements would be one of them, but there are other approaches as well. And we've talked long and hard about how to bring uncertainty properly into bear on this, so that we understand the limitations of the models, and then how we might integrate data into models like that. Do you know what I mean? And thus, I guess, create a taxonomy of, or even a roadmap in some sense, about how we might address these sorts of key theoretical problems and genuinely develop a new paradigm for engineering computation, for argument's sake. And yet at the other end, you and I have spoken about the fact that I think some of the hardest problems are not in any of those one areas. They're in things like systems. How do you model an aircraft carrier or a big chemical process industry or something like that? What's the right taxonomy? What's the right mechanism that we can bring all these things to bear? Do you know what I mean? At a theoretical level, at least.
So, I think, so it's absolutely clear, and this is nothing new. I mean, this is just going back to the 17th century. There are the microscopic, the mesoscopic, and the macroscopic views. And, just think of Poisson's equation. It can be used to describe heat conduction at a microscopic level. It can be used to describe fluid flow, Darcy's equation. It can be used to describe, deflection in continuum solids and so on. So those continuum, PDE, ODE type descriptions, very classical, are the sort of go-to tools that what one uses in describing phenomena such as fluid flow, continuum deformation, and so on. The theory that has been built up over the years has been largely devoid of the notion of uncertainty. And so that then places, unwarranted faith in the fact that this macroscopic description is, is absolutely faithful to whatever it's trying to describe. Now, of course, there's the whole area of stochastic differential equations and stochastic partial differential equations, which then gives a way into describing the fact that the equation does not capture all of the phenomena at a particular scale. So I would say stochastic modeling, both at the macroscopic level, and then, at the microscopic level, we pretty much are working at a stochastic level, where we're modeling particles and their interactions in some way. So I would say that taking all of that work and embedding it within either a stochastic calculus or a probabilistic calculus, and then further out with a statistical framework, it is probably the way to go. It's certainly what we have done. Our teams have taken the whole notion of numerical analysis and said, this isn't a deterministic process. It's a random, it's a probabilistic process. And that argument comes, basically from, optimal, game theory. And then, immediately you've now got a calculus that allows you to take data into account when you are, trying to numerically solve PDEs, ODEs, what have you. And then, so that's probably my answer in terms of what the taxonomy would be, is stochastic, probabilistic, and statistical. And and there may be some people here, a lot of numerical and functional analysts just hate that idea, but it's a very natural one that you take, a classical Hilbert, a linear Hilbert space of functions, and endow it with more structure. A Hilbert space is just a Banach space with more geometric structure. So why not take the Hilbert space and endow it with, structures to do with measures and embed probability measures into it. So these are not new, but I think in terms of formalizing these ideas, it really gives us that taxonomic way of constructing how to assimilate data. And I wouldn't even say it's assimilating data into these, but it's actually constructing the overall data-centric, mathematics-driven representations. So that the data is no longer just an addition, but it's actually a core component of the representation that we're trying to characterize and analyze and fundamentally use. I don't know if that's answered the question, Hugh.
Well, we'll have a beer at some point and answer it in more detail.
Yeah, it definitely needs a lot more detail than than the time that we've got available.
Okay, Ben, you're next.
Hi, Mark, and thanks for a very interesting talk. I've got a question about the collaborations with Rolls-Royce. Now, Rolls-Royce have got a huge amount of experience in vehicle health monitoring and instrumentation of engines and getting an enormous amount of data. How have you found that interaction, and how have you, I guess, intersected with that very developed process?
So, Rolls-Royce kicked this whole thing off in the 60s. And the power by the hour business model that they adopted was way back in the early 60s. And they were able to use that, or they were able to employ that business model, just exactly as you said, because they were instrumenting their engines at quite astonishing levels. And so Rolls-Royce are probably one of the most mature businesses and aerospace, the sector, that has been taking a data-centric view. And I have to say that I for one thought, well, we probably don't have much to teach these guys. As you know, at Cambridge, Rolls-Royce have the Whittle laboratory. And one of the group leaders that I recruited was actually a Rolls-Royce research fellow. And so one of the big questions they have now, and they're trying to grapple with, and this leads on from modeling a thing, or representing a thing, has one degree of difficulty, but modeling something that is comprised of discrete elements that interact in some way that's weak or pretty much undefined is much more challenging. And so one of the things that Rolls-Royce are really being driven by is to say that we don't just have engines, we have fleets of engines, and we have our engines are on fleets of aircraft. And so our customers are really interested in managing their fleets, not just managing their engines or managing an aircraft. So we're working with them on trying to understand, again, how do we capture what a fleet does, and what are the interactions in the components of a fleet. And they're very open to this, and we're working with them actively. The other area that Rolls-Royce are really keen on pushing is using the data that they have to support their design process. And so we've been working with them on a specific area, which is the design of fan blades. As you know, the variability of the manufacture of fan blades is for their purposes, is really difficult to control. And so, looking at different types of blade envelopes and looking at the design space and moving away from 50-dimensional design spaces to ones that we're really capturing the active, as it were, design subspaces. Is work that has come from us along with them, and that they are now adopting as part of their design for manufacture process. So even though Rolls-Royce have been at this game for over half a century, there are still huge problems. I mean, one of them is when they do performance calibration, they'll instrument to death an engine, put it on a rig, and then get all of their characteristic curves. As soon as they put that engine under the wing of an aircraft, the difference between what is measured on a rig and what they actually see in operation is so vast that they're still grappling with how to make that difference something that is manageable. And the Whittle laboratory, and we're working with the Whittle, is looking at those sorts of issues.
Okay, Ian, sorry, Ben, did you have a follow-up, or?
I was just saying thank you.
Oh, okay, sure.
Yeah.
Ian.
Hi, Mark. Thanks a lot for a fascinating presentation. It's really impressive what you've built over there. My background in research is kind of in control systems and algorithms for state estimation, particularly for nonlinear systems and so on. So I guess, outgrowths of things like the Kalman filter, where you're fusing data with mathematical models. So I'm definitely on board with the whole philosophy that you're espousing. I have a question about, I mean, when you take these ideas of kind of state estimation, data, you know, assimilation of physical models and data, but you're talking about PDE models for fluids or for structures. So they're, you know, in principle, infinite dimensional state spaces, or with a finite element model, finite but very large dimensional state spaces. Typically non-linear, so you probably shouldn't really be trying to quantify uncertainty with Gaussians and hoping that it works all the way through like you can with linear cases. So I'm kind of wondering, so I guess, you know, the other way people often do things is through kind of particle or Monte Carlo methods, but then when you're talking in extremely high dimensional spaces, you can never have enough particles to really span the space. So I'm just wondering, kind of on the technical front for dealing with high dimensional stochastic nonlinear models and actually trying to do kind of the uncertainty propagation properly but computationally feasible. I mean, have you seen any kind of emerging ideas or any, I guess, is there kind of any hope there? Because it seems like an almost intractable problem to do it kind of properly, I guess.
Yeah, I mean, so you're absolutely right. I mean, these are infinite dimensional spaces that we're dealing with, and even, you know, projections, you know, down onto finite dimensional subspaces, they're still very, very high dimensional, and that pretty much precludes Monte Carlo particle type methods. The work that we've been doing with the statistical finite element method for time evolving nonlinear PDEs, we used solitons as a working example, and this was a collaboration with the Oceans Institute and the Offshore Structures Institute over at University of Western Australia. We looked at a number of things, you know, classical nonlinear Kalman filters. But the thing that really struck us was ensemble Kalman filtering. Empirically really worked well. And so one of my colleagues at Caltech, Andrew Stewart, he has been doing an awful lot of fundamental work on trying to theoretically characterize the ensemble Kalman filter. I mean, you know that the ensemble Kalman filter was, you know, weather prediction and meteorological modeling, and the theoretical basis for it is flimsy at its best. But empirically, it really allows us to tackle these really high dimensional state evolution style problems. And so I think one of the things that's really most promising is to then take these empirical methods and actually, you know, throw some tame analysts at them, such as what Andrew at Caltech has been doing, and really trying to, you know, understand and what are the levels of analysis, mathematical analysis that can be brought to bear on them to give us insights as to what the fundamental theoretical properties are. Because I think you're right, you know, this is just such a hard problem that, you know, starting with a clean sheet and working from the ground up is well, we could be waiting quite a long time to make any progress. So taking empirical methods that clearly seem to work, and trying to understand them is probably a good way to go.
Do you think the ensemble Kalman filter is kind of finding lower dimensional subspaces or manifolds with the ensemble?
Yeah, I mean, I think that's one of the things, and you know, that's another area of work that I'm involved with is this whole notion of submanifolds, and how we actually characterize and then subsequently exploit those, you know, so that the data or equations, you know, functions actually reside on submanifolds rather than in the actual ambient space. And so it certainly seems that, you know, given the nature of the ensemble Kalman filter and the kind of local estimates of covariance structure, you could almost, you know, in a very ad hoc way, you could almost think of that as, you know, learning the local metric tensor of some submanifold.
Okay, fantastic. Thanks, Mark.
Sorry, when I said learning, I meant estimating.
Sure. Got to choose your words.
Learning sounds so much cooler, Mark.
Yeah, no, it's just that there's a workshop on the theory of deep learning here at the Isaac Newton Institute in Cambridge, and I've been going along, so that's why the word learning slipped in there.
We'll forgive you.
Thanks.
Well, we're just on 5 o'clock. I don't think there are any more questions at this point. Any last questions?
No.
So perhaps I can say thank you, Mark, for a fascinating talk and giving us your time, and then also for a really engaging question and answer session.
One thing, just before we go, so Mark, enrolling, so this DCE Summit event, is there a way for people who are on the call, for example, who might want to be part of
If
that,
you email
or something that's going to be?
Yeah, if you email me, I can give the details for how to you know, how to join.
Okay, that would be great.
Actually, I should also say that the organisers are trying to contact both you and Hugh to be speakers at it. So have a check in your email.
Yes.
Yeah, no, I've seen it. I'm actually planning to see whether I can get Matt to do the talk instead, because he has many more interesting things to say than I do.
So just finally from me, I would absolutely love to talk with you and to both at a research level, but also at an organizational level in terms of you know, whether it's helping you establish something at Sydney or grow. You've established it, but growing it, and you know, collaborating with us in the UK and elsewhere, and just building this kind of global, you know, data-centric engineering movement.
And to that end, Mark, to that end, Mark, there are many people from Data-61 on the call, because they've got a big interest in this area as well. So we've talked about maybe the Turing and Data-61 sort of having some collaboration on this area, which would be great.
Yep.
Yeah.
Yes, Matt, I will. I've seen the email. Sorry, Mark, I've seen the email and I will respond.
I've already responded. Right. Thank you so much, Mark.
Thank you, Mark.
Really appreciate it.
Great stuff.
Great.
All the best.
Bye.
Thank you.